Okay, let's begin. So it's a real honor and pleasure to have Anna Iljas, who is visiting us. Anna is currently visiting at Harvard, but she is the principal investigator for the Simons program in cosmology. Anna started life off actually doing a PhD in the philosophy of quantum mechanics, and then moved over to doing a PhD in physics. Actually, even though she's going to talk about she's a cosmologist, but she actually did a PhD under Herman Nicolai, who was a supergravity pioneer. One of the, if Professor Gates is here, he'll shake his head. And did her, I guess, first postdoc, at Princeton. And now she's now going to tell us about the Big Bang versus the Big Bounce.
Thanks, Stefan. Thanks for the invitation. It's great to be here. It's a great honor. So what I will be talking about today is the question, what happened 13.8 billion years ago? Obviously, this is a question that we all should care about, since everything what we see today in the universe relates to this one event. Now, traditionally, and perhaps most of you assumes that this event was some really violent event that we usually call the Big Bang. And that is somehow related to a beginning of everything, including space and time. In my talk, what I want to convince you about is that there is a really interesting alternative that says farewell to the Big Bang and the idea of a beginning altogether, and replaces it by something that we will be calling the Big Bounce, transition from a previous contracting to an expanding phase. Just to clarify things here, because some of you might be scary how esoteric I might be. Obviously, when I say I replace the Big Bang, I don't replace anything about what we call Big Bang cosmology. Big Bang cosmology is, and this is just a misnomer for it, is describing the evolution of the universe that we understand very well, that started, say, around nucleosynthesis, and this is what we call Big Bang, what astronomers, cosmologists, high-energy physicists, everyone calls Big Bang cosmology, is just the phase from which the universe expanded at a decelerated rate, and this is the phase that we really very well understand. I will talk about the phase that we don't understand. And let's start with our universe as we see it today. This looks like this. Our local universe today is a patch. It's a maximum distance of as far as we can see. And we know that our local universe is denoted with an associated value of A, the scale factor of 1. And we know that our local universe is really complex. It's full of galaxies, stars, planets, black holes. So it's not simple. However, we also know that it originated from something that was very simple. As simple as you can imagine. So if we extrapolate backwards in time, trace back our local patch to a size when it was a thousandth of its current size, more to that later, then to first approximation, it looks like something that has no structure, nothing. It's very simple. And it's characterized by a single temperature, which we today call the temperature of the cosmic microwave background. And so what we have to explain in cosmology is, what gave rise to such a simple universe? Now, the universe is very simple, but not completely simple. If we want to look for deviations in terms of temperature from the mean temperature, we have to go to the level of a percentage of a percent, namely, we have to zoom in by 100,000 times, and then we see anisotropies, deviations from the average temperature. And that you see in pictorial as blue, cold spots, and hot spots of the microwave background. And what we know is, thanks to our experimental colleagues, that not only are the deviations from the average temperature extremely tiny, having an amplitude of 10 to the minus 5, they also are what we call nearly scale invariant, their distribution. So at all scales nearly the same, and the statistical distributions of these deviations is the simplest that you can imagine. It's Gaussian, or nearly Gaussian. So this is, some of my colleagues say, is the simplest possible universe that we can imagine. And this is on large scales. And this makes it difficult to explain, because by one measure or another, you would like to have a simple explanation for a simple universe. Now, cosmologists have been struggling with this, in particular early universe cosmologists as me, for about 40 years, since the late 70s, early 80s. And what I want to talk about first is, why is it so difficult to explain what gave rise 13.8 billion, or a little bit later, billion years ago, to this simple structure? And what I could start now with is, I could just start to write down the Friedmann equations, which are the solutions to the Einstein equations evaluated to our universe. But that's not what I'm going to do. What I want to do is leave off equations and show you a diagram that I call the wedge diagram. The wedge diagram has the following features. We are already familiar with the scale factor that explains the rate, or tells you the rate at which a universe going forward in time expands, or going backwards in time contracts. And normalizing it as 1 today, it will also serve as our time coordinate. Going backwards in time and expanding in an expanding universe, A will shrink. And if today it's 1, and if I wanted to move forwards in time from today, then obviously A would grow. These are the edges of the wedge. And the arc that connects the wedges will be the size of the universe at the time at which I'm looking at it. So this would be the universe today, associated with a scale factor of 1. If I extrapolate backwards in time, a smaller arc will correspond a smaller patch as the universe was back then in time, corresponds to smaller edges. And I could go further, backwards in time, and I would get yet smaller arcs. Now, obviously, I could have done, nobody told me that today I should draw a wedge that it has exactly an arc corresponding to it by 1. I could have drawn you narrower wedges, and I could have drawn you also wider wedges. This would just have corresponded to narrower or wider slices. What I want to tell you with this is, the scale factor doesn't tell you yet anything about physics. It just tells you something about the geometry of the universe. In a universe that is homogeneous and isotropic, so very simple to leading order, the scale factor just described that this corresponds to the scale factor being the single dynamical parameter describing such a maximally symmetric universe. But obviously, we know the physics that describes the universe for most of the time, most of cosmic time, and this is general relativity. So general relativity tells you 2 things. The first thing is that if you really follow a universe as ours, backwards in time, then all edges will focus in one point. And this is the point that we usually call the Big Bang. Now, obviously, this is too nice of a name for an event, because what we really should call this point is the singularity problem. It just tells us that extrapolating, in some sense, too far backwards in time, the Einstein equations, the description of our universe as we know it, as it works for us, break down because temperature, energy densities, and curvature will grow to values that are non-physical. They are singular. And this will be denoted in this diagram by the fact that in standard Big Bang cosmology, assuming Einstein relativity, you end up with a bang. This is a problem. This is not something that we should take as a feature. This is a problem that we as cosmologists have to resolve. And there is a second feature that relativity tells us, namely that the scale factor that describes the geometry of our universe is not the only scale that exists in this model. There is a second scale. And this is, for the purposes of this talk, I will call it Hubble horizon or simple horizon scale. Roughly speaking, this is the furthest distance as far as you can see at a given time. So today, the arc, the size of our observable universe, also corresponds to our horizon size. But, and here comes GR, and this will be what all the problems in cosmology boil down to, tells you that the horizon doesn't evolve linearly with the scale factor. For a universe that is filled with ordinary matter or radiation, the horizon scales differently, namely with the scale factor to the power of something that I will call epsilon. And the only thing that you need to know for the purposes of this talk is that for radiation, so starting out from a hot bang, the horizon scale, so the scale of causal connectedness, evolves faster than the horizon. And it continues to be so when matter takes over. It is still faster, since 3/2 are greater than 1, but a little slower than radiation. Now this leads to the fact that if we want to draw the evolution of the horizon scale, that moving forwards in time, the horizon goes really fast, and moving backwards in time, you see, the horizon becomes quickly much smaller than the size of our physical patch. And again, just to repeat it, the very fact that such a horizon size exists is due to general relativity. If there was no relativity, if our universe weren't relativistic, let's say if it was Newtonian, then we only had one scale, and there was no limit as to how far I can see or how far I can go without issues backwards in time. Now, on the one hand, this is a neat feature. On the other hand, this is a problem. In particular, for cosmologists, this is a problem. Since recall what I was stressing in the beginning of my talk, our universe is very homogeneous. Now let's track our universe a little bit backwards in time once again, but looking now, trying to figure how the horizon evolves. You see, if we track back our local universe just a little bit in time, let's say when it was when the scale factor was half of its size today, then what you see is very quickly the horizon, the observable universe, what we can see backwards in time, entails a lot more than the size of the horizon was at that time. And that really is a problem, because if you move further backwards in time, in particular to the time when the cosmic microwave background was emitted, so to the time of when we see the cosmic microwave background as the last scattering surface, when photons last scattered off of electrons, then what you see is the horizon was a lot smaller, exponentially smaller than the patch that you can see. And the fact that the region, first of all, looks so similar over scales that are much bigger, much bigger, exponentially bigger than the scales that could have been in causal connection, could have causally interacted with one another, is called, and some of you might have already heard of it, the horizon problem. Now this is very often associated with or named was as a smoothness problem. So the fact that the universe looks everywhere the same, even though it could not have been in causal connection. Now there is a second problem that you cannot exactly see from the illustration, but I also mentioned in the beginning of my talk that those the distribution of the tiny hot and cold spots in the microwave background is a very particular one. So it is smooth only on large scales, on the larger scales, but not perfectly smooth. There are these cold and hot spots with a very particular distribution. And if you ask me how big is the maximum or some average size of those hot and cold spots, what you would have to see is that some of them are bigger than the horizon size at that point. So not even the hot and the cold spots can be explained, or their homogeneity, by causal physics if you only use relativity. And this is called the superhorizon hot and cold spots problem. And there is a third problem in an expanding universe. And this is, again, some of you might be familiar with it. It is called the flatness problem. The flatness problem related, again, to the fact that the radius of curvature scales with a scale factor. In other words, think about it, you are sitting on a plane. You usually see a little bit of a curvature, right, on the horizon. If we are on Earth, we don't see that. Why? Because our horizon is so small. That was the reason why people for a long time, because their horizon was both in the literal and abstract sense limited, that's why they couldn't see the curvature of the Earth. That's why there were flat earthers for a long time. I'm not quite sure why there are still many of them, but that's a different problem. The point that I want to make here is that if your horizon grows, especially if it grows faster than the radius of your curvature, your scale factor, what you should expect is that you see lots of curvature. Just as when you go on a plane, or if you are lucky, you go on a rocket. You should see lots of curvature. But what we measure when we go out and measure from the temperature and isotropy, hot spots and the cold spots and their distributions of the cosmic microwave background, we can also deduce that the spatial geometry of our universe is not just homogeneous and isotropic. A homogeneous and isotropic universe could be curved or flat. But our universe is flat. And this is not what we would expect. There is no reason to expect, if your horizon grows, not to see any curvature. And this is one way of understanding the so-called flatness problem. So these are the famous problems: the singularity problem, the horizon and smoothness problem, the superhorizon hot and cold spot problem, and the flatness problem that cosmologists have been trying to solve for about 40 years. And the traditional solutions has been exactly what you can read of when you look at this wedge diagram. So all the problems can be traced back to the fact that during the evolution of our universe, the universe is dominated by radiation first, and then by ordinary matter. That causes the horizon to go faster than our physical patch size, meaning that everything what we see today couldn't have the same causal origin, if that was everything what happened during the evolution. So the idea was, could there have been a phase during between the bang, whatever happened then, and before the phase of radiation domination started, that for now we only have to know as much about that there the horizon scaled as a square. Could there have been a phase where exactly this relation was different, so that the horizon scaled or evolved at a slower rate than our physical patch? And this is exactly the idea of inflation that was introduced by Guth 1981. Imagine a phase, a very early phase, before radiation domination took over, where some form of energy dominates the total energy density that can be associated with an epsilon number that is smaller than 1. If that's the case, then you can grow the physical patch size very rapidly. That's why the name accelerated expansion, while your horizon size remains nearly the same. The smaller epsilon is. And this is really inflation. Now, this won't be a talk about inflation. Inflation has taught us a lot about cosmology, but we also learned one particular fact about inflation. And this is something that one actually always knew. The fact that inflation doesn't solve the singularity problem. Now, the original idea was that whatever happened at the bang, the inflationary physics should wash it away in a way that naturally explains our universe, that is, puts things into causal connection, smooths things out, and, to that a little bit more later, generates the right spectrum of superhorizon hot and cold spots. What we learned is that it's not quite the case, that inflation is not entirely insensitive to the singularity problem, that it very much matters how you explain the fact, especially if you assume a beginning, how the universe came out a quantum gravity-dominated phase, classicalized, and ended up with a certain type of geometry dominated by a certain type of energy density, both just the right kind to start inflation. And that's why it's so important to work on the singularity problem, because if you want to explain why inflation is a natural outcome, you need a solution for that problem. But you might not want to explain that inflation is a natural outcome. You might ask a different question. If the singularity problem, or how I resolve the singularity problem, is so intimately related to the fact that there are these problems arising, and the so far really one standard and good-looking solutions under certain aspects is sensitive to this problem, you might want to ask the question, am I stuck with a beginning? How would a solution look like to the questions, to the problems that arise in standard Big Bang cosmology, assuming a beginning, if I replace the bang with something that I call a bounce? Now, what does it mean? First of all, in terms of the wedge diagram, I would not stop with a bang. And to this phase a little later. For most parts of my talk, I want to convince you that assuming what you would always assume about any pizza or pie that consists of wedge, that you have many other wedges, or at least one other one in the opposite side, is an interesting possibility. And look at that, what happens. First of all, I don't have to stop extrapolating backwards in time at the point where all edges would focus in one point, but I extrapolate further back. And this phase, you see, has a different dynamics. In some sense, the opposite dynamics as the expanding phase. It contracts. So you start with a moving forwards in time. You would start with a large scale factor, and as the universe contracts, the scale factor would become smaller and smaller. So first of all, your physical patch would become smaller, again linearly with the scale factor. But there is a second, and this is also important, a second aspect to this story, namely how your horizon size evolves. You recall that the problem was that the horizon size was moving forwards in time in an expanding phase, always scaling faster than the physical patch size. All problems really relate to this one single fact. Now, what you want to have here now is the following. You want to have the opposite behavior. You want that your physical patch, what you see here today, our local universe, when you extrapolate backwards in time, you find that this patch has always been part of one single horizon. And how can you reach this? Obviously, you don't fiddle here. This is just what I called in the beginning and defined for you as our Big Bang cosmology. Where you want to fiddle is here. What do you need? Do you need that? First of all, what you want is, again, it cannot be the same behavior. But what you really want is that moving forwards in time, the horizon shrinks much faster than the physical patch size. Because if it shrinks much faster during this contracting phase, what you really reach is that moving backwards in time, it has grown much faster. So it was very quickly, again, this is just a schematic illustration, it was very quickly, your horizon size was much bigger than the physical patch size, much, much bigger. So that's why epsilon being greater than 1. Obviously, those who were watching out of you know that it has to be at the very least smaller than 2,2, so that it beats the radiation epoch. But for now, it's just important. We can, most of the time, take, let's say, 10, 20, 100, whatever you wish. But it turns out it doesn't have to be all that big. Doesn't really matter as long as it's bigger than 2 or 3. So the first thing what is solved immediately is the horizon and smoothness problem. Just for the reason that the horizon size has always been bigger if you trace back our local patch. It always originated from an epoch where the horizon was much bigger than your physical patch size. Now, this is really important that you watch out. We didn't just reverse the evolution. This evolution here is different. It's not just contracting at a certain rate. It contracts the universe, especially the horizon, undergoes a contracting phase where the scale factor, as opposed to the horizon, contracts much slower. That's why it's named slow contraction. And you also solve by the same token the flatness problem. Because if you start from a horizon that is really big compared to your physical patch size, no matter how well you zoom in, you remember this was a zoom in, zoom out problem about whether if you zoom out a lot, you want to see curvature. But if you imagine what we did here backwards, we zoomed out we zoomed out so much that no matter how well you zoom in later, you cannot see curvature. You just cannot see it because this is the horizon evolved, just shrank in so much faster than the physical patch size shrank. So these are the classical problems to flatness, horizon, and smoothness that you can solve just by the simple assumption that there was a contracting phase where the horizon evolved shrank at a much faster rate than the scale factor. Now, this is so far neat, but there are two more questions remaining, which are really important. In fact, those were especially the superhorizon hotspot and cold spots are the question. If you cannot solve them, you can forget about your scenario. But before I get there, I want to show you something. So very often, and really it's the case that most cosmologists, you imagine them, they are particle cosmologists. In fact, cosmology grew up as a science by particle physicists in the 80s coming into cosmology and solving certain problems that just by doing GR couldn't be solved. So it's a good thing. On the other hand, there are certain questions that you cannot really answer without, and I already made some points of it, without considering the fact that we really live in a relativistic universe. And very often it gets forgotten that we are not just relativistic, we are deep in the nonlinear regime of general relativity. So just like with black holes, the fact that we can do so much with pencil and paper and cosmology is not due to the fact that we are not in the nonlinear regime. Just think of the Kerr solution or the Schwarzschild solution. It's the same situation here, the Friedmann-Robertson-Walker solution. It's an exact solution of the field equations. And because we have an exact solution, therefore, we get very far with just doing little perturbative calculations, which are non-trivial, to be honest. But still, we can get very far with pencil and paper. But not because cosmology is not very well in the nonlinear regime of GR. However, if you're a cosmologist, you ask a second question, especially if you're an early universe cosmologist. How generic is your solution? So we have an exact solution. We know that we can use the exact solution because it describes today's universe. We can see what happens, and that's what I was showing you, for example, with the flatness problem. What happens if we go a little bit away from the Friedmann-Robertson-Walker solution? But we don't know. What if the universe started really far away from this exact solution? Then nothing what I have shown you should be a priori valid. Because we don't know how the Einstein equations behave for arbitrary geometries without computers. So if I find a phase, be it inflation or contraction, that does a lot of things classically really well, if I go a little bit away from a Friedmann-Robertson-Walker solution, and that's what I was showing you, you want to ask a second question. What if I started really far away from that solution? Because that's my real question as an early universe cosmologist. Would some energy density that I add into my space-time to start this contracting phase, would this work for arbitrary geometries? And that's what you can do by exactly using the same methods that people use to simulate black hole singularities, or mergers too, but so that one studies LIGO. And what you see here is exactly such a simulation. You see here, and this is current work under in preparation with my collaborators, two relativists, Garfinkel, Pretorius, and the cosmologist Steinhardt. What we do here is we put the universe into a box. What you see here is a 3 + 1 dimensional universe, but we evolved the inhomogeneities only in one direction. And that is what you see. This is the x direction. And what you see the white, so that is a spatial direction. You see a box of a 3-dimensional universe. Nothing interesting is happening in 2 spatial directions, but a lot of interesting things will be happening in this, one spatial direction. And what you see here is on the y-axis, we have normalized energy densities. So what I want to show you is, when we start with a universe dominated with some real mass, and this is what we call shear, so deviation from homogeneity and isotropy. And you see it's a lot. So we just start with some random geometries that should not look like at all as Friedman, Robinson, Walker, as homogeneous and isotropic. We add in curvature here. This was just the same, would be the same contribution from the geometry that causes the flatness problem in expanding universe. And then we add in some sort of matter. This is not ordinary matter, but is representative for the matter energy density that should be causing, in a Friedman-Robertson-Walker universe, the horizon to be shrinking at a much faster rate than the scale factor. Okay? And if I run this simulation, I want to see the following. I want to see that yellow takes over, because if yellow took over, at least in lots of parts of space-time, so this is my original patch, then it would mean that most of space-time was smoothed out and converged towards a homogeneous and isotropic metric, because I suppressed all the contribution from geometry, flatness, and shear that could have messed up my geometry. So let's look at this simulation. See, something wild is occurring in one region. So what you see is, if I run the simulation, this is, I solve the full Einstein equations with really messy geometry. Starting with really messy geometries, you see there is one region that's looking very good. First of all, you see that nowhere is curvature important. And this is exactly due to the fact that curvature gets very, very much suppressed because it scales with the physical size of the physical patch linearly with the scale factor, while the horizon size rapidly shrinks. So you can have no chance to see the curvature. These are the good regions, because they are dominated by the smooth, homogeneous scalar field matter. And these are bad regions, because they are messy. They are dominated what we call shear. And now you want to ask, what fraction of these bad regions is bad? What fraction of them is a fraction of the total volume? And you can measure that too. Now you recall that the horizon was the important quantity. And it was the scale. So it was sort of a length scale. And what I can do is, if I want to measure volume, or proper volume, is I just take the volume integral, but now the relativistic, or for experts, the covariant generalization of the horizon, and measure it. Horizon was, so this is what I exactly can measure. And there is a natural, so again, for experts, it's called a lapse. This is the measure of inverse volume. So it's exactly what I will show you is, I denoted the horizon skies with h minus 1. I will now show you the volume integral over h. And this is just the inverse volume measure. And what you will see here is the same box. And now you associate shear-dominated regions with a certain inverse volume, and matter-dominated, good type of matter-dominated regions with a certain volume. And what you see here is that the bad regions, the pink regions, have huge inverse volume, which means they have small volume, in simple speaking. And that's good. So what you have found, again, I just want to stress, if you want to ask, what you showed us in this wedge diagram, that was neat. That tells you if you start close to the right kind of geometry, taking care of the fact that an energy density dominates the universe during a contracting phase that causes the horizon shrink much faster than the physical patch size makes you smooth and flat. But what I have shown you is you don't have to make that assumption. You don't have to make the assumption that you are close to the right kind of geometry. You can use the full power of numerical general relativity and show that classically a contracting phase that's filled with an energy density that has this really large epsilon, which corresponds to, really, just to tell you, large pressure. So large pressure, maybe the scalar field or some other condensate, will drive you generically towards the type of geometry that we have to see. So this is something that we could never do with pencil and paper. And this is a this is, let me just emphasize it. This is something that we couldn't yet shown. Nobody could have shown in this genericity for inflation. In this genericity is what not possible. So I find it, when I saw this first, that this is really the outcome, I find it personally really intriguing. Now, of course, you ask me now, but how about those hotspot and cold spot? Because we just super smoothed our universe. So we have a really smooth universe that looks everywhere the same. But we know we don't want to have a super smooth universe. We want to have a universe that is nearly smooth and has the right kind of inhomogeneities. And without getting into technical details, let me just mention you this much. There is one feature that comes out really automatically of this slow contracting phase. That whatever you do, the inhomogeneities will be on superhorizon scales. And again, at the risk of repeating myself too often, the only reason being that your horizon shrinks at a faster rate than your physical patch size. Let's start with a huge horizon. Remember, we started with a horizon size that was bigger than the physical patch size, the contracting phase. And we will start with some inhomogeneity. Let's imagine we are in Fourier space, that the mode evolves with the physical patch size, so linearly with the scale factor. So what do we expect? We expect that very quickly the horizon will shrink in on the mode, because the mode cannot keep up with the rate of shrinkage. You see? That's what's happening. So again, this is just a simple illustration, but what this relative rate of contraction gives you is that starting with subhorizon inhomogeneities becomes superhorizon at the end of contraction. And just for those who ask me, well, you didn't really tell us how inflation does it. This is very similar, and I find that intriguing. So the classical story of inflation with respect to the superhorizon modes is very similar. In inflation, do you remember what I said was the horizon had to be expanding at a much slower rate, a to the epsilon, where epsilon was much smaller than 1, than the physical patch size. So what happens there is if you start with the subhorizon mode, and you keep your horizon nearly frozen, again for experts nearly de Sitter, it's almost like a cosmological constant-dominated phase as we experience it today. The modes will just rapidly leave the horizon. So the same idea, the relative expansion rate, but with a very different underlying dynamics here. Your horizon zooms in, and in inflation, the modes just go out like crazy. So the classical story of these two ideas is similar, where so far the real difference is that we could show for the contracting phase that it's extremely generic, classically. You can start arbitrarily far away from your preferred metric, from your preferred geometry, and this phase just drives you there. You cannot help it. And once you start with inhomogeneities, they will become superhorizon. Now for completeness, I should also mention this is really both classical stories, inflation and contractions, are super smoothers classically. So what you need to have at all inhomogeneities is you have to assume, and we know that this is not an assumption, this is something that we always have to count with, that quantum physics never makes anything perfectly smooth. So the only thing what you have to take into account in cosmology, and we can do this without knowing any story about quantum gravity, that every degree of freedom experiences quantum fluctuations. So the geometry, the curvature too. And these quantum fluctuations will become due to the relative motion of horizon and physical scale, superhorizon. And that's why many people say that we all originate from quantum fluctuations. And this sense is probably true whether you believe in the contracting phase or an inflationary rapid expansion phase. However, there are two notable differences. If you ask me, what is a definite prediction apart from the smoothness and flatness that can make your model vanish? I'm a physicist, so I'm interested in theories that can be proven wrong. And therefore, I want to know what would I need to measure that would convince me that what I'm doing is definitely not an explanation for what I observe. And this is what I'm going after, or many of us are going after now, is the so-called primordial gravitational waves. So there are gravitational waves measured by LIGO. They are generated due to the merger of black holes, of stars, or stars and black holes, neutron stars or neutron stars and black holes. But there is in the initial, so this was one of the recognitions in the 80s again, or if you wish even a little bit earlier, 79, that in the cosmology context, in relativity obviously earlier, that if you shake space-time, then not just the energy density, so the scalar degrees of freedom are being shaken, but every single, just as I said, quantum physics doesn't distinguish between degrees of freedom. All degrees of freedom are being shaken. So the gravitational waves, or the so-called tensor modes, tensor degrees of freedom are also being shaken. And the higher the energy, the more are being shaken. As a matter of fact, if you take the simplest inflationary models, then most of them predict a relatively high amplitude. And we know that we can measure them. In fact, most of you probably heard of the Bicep 2 incident. People thought a few years ago to have measured them, and that would have been, some people call them, definite sign of inflation. Now, that should be taken with a grain of salt, probably, but the main point what I want to make here is there is no natural way in these slowly contracting models where the horizon rapidly shrinks in relative to the patch size, exactly due to the fact that the energy densities are relative to, let's say, an inflationary phase lower. There is no simple natural way, nothing without doing something really nasty that probably you don't want to do to your theory, to generate detectable gravitational waves. And this is important because these experiments are under construction that can get to a level where you want to see inflationary modes. And one experiment I'm actually part of is the Simons Observatory collaboration. Should see first light in the next 2 years. That should go down to a level where the next simplest inflationary models can be detected, and definitely should go down to the level CMBS4. So if at those levels gravitational waves are being seen from the primordial phase, these models are out. If they are not seen, I think that's a good news in the sense that you would not expect them if these models are true. So either way, we win. Now there is a second feature of some early universe models operating within the context of inflation, actually all of them, that most of you might have heard of, whether from the popular press or from cosmologist colleagues. And this is the so-called multiverse effect. Now, I prefer to call it quantum runaway for the following reason. And this is related to the fact that you cannot ignore quantum physics, whether it comes to the rescue or whether it tells you something bad. So what we do again in cosmology is, short of being able to explain how classical metric emerges from a quantum gravity state, we always assume, for the time being, that the leading order of metric is well described by classical physics. And where we assume that quantum fluctuations affect these metric and the scales and the energy densities are always the fluctuations. Now, good news is that small fluctuations can be thought of as small time delays. That means whether you contract or inflate, these small quantum fluctuations would lead to the fact that contraction or inflation stops at different parts of space-time, just slightly different times. And these slightly different times of stopping contraction or inflation lead to these tiny anisotropies convert into these fluctuations in space-time, in the geometry, in your energy density, to the temperature fluctuations in the microwave background. That's the good news. However, when you expand, you have to also, and also when you contract, but there it won't be bad, just to take it away or give it away, you have to also think about the fact that not all quantum fluctuations are small. There are relatively rare fluctuations, if you follow the story literally, that would delay the end of inflation by a lot. And those patches would have expanded exponentially more. And those patches that expand exponentially more would not just expand exponentially more, but rare fluctuations in those patches would again expand exponentially longer, and so on and so on. And this is what people call eternal inflation, a multiverse effect, that lead to the fact what Alan Good said leads to a multiverse where everything that can happen will happen, and it will happen infinitely often. So if you take it literally, you have to deal with this fractal multiverse feature. If you don't take it literally, you have to deal with the fact that you don't know what to do with the large quantum fluctuations. Now, the contracting phase has a different story. And the story here is that what happens, it's very simple, it's a one-sentence story. What happens with the large fluctuations that delay parts of the patch finishing contraction? Well, they will reach, what I will be talking about the last remaining 4 or 5 minutes, this transition to the expanding phase later. What does it mean? Those rare patches that doesn't look like us will have expanded by now less. So they are volumetrically less. And what does that mean? That we are typical in this scenario. So there is the rare quantum fluctuations doesn't cause, at least volumetrically, and by no other natural measure that I know of, rare patches that don't look like us take over in volume or in other natural measure. And in this sense, that is the other feature that's distinguishing from the inflationary expansion. You don't have to deal with, whether you like it or not, with the multiverse effect. So again, I'm not saying here that it's necessarily something that you should dislike, but it's important to know that you are not stuck with the multiverse. Now, let me close with the biggest problem. I'm standing here in front of you and represent or try to convince you of a scenario that obviously in the moment is a minority opinion. So you might ask, if this is so generic, if you haven't done anything to your gravitational theory because you really just were following general relativity, you have no funny matter because most of the time, I should tell you this phase is realized by a single canonical scalar field, just like inflation. You have no multiverse effect, and you can make a definite prediction, definitely one, that is this is distinctive of this scenario. Why are not most of your colleagues believing this? And the simple answer is this. So I told you the story, and this was really the main point of my talk of this phase. We understand this phase very well. It's a simple phase, and it leads there where we want to be. And that motivates us to work hard next. And because what the non-trivial part of this story is, and this is a lot less well understood, and I want to be here honest, I don't want to tell you something at a stage where it's not yet. It's a lot less well understood, but we made a lot of progress lately. How is a transition possible from a contracting to an expanding phase, which we call a bounce? Because one thing we know, we cannot do Einstein gravity. And I want to close just with a few words about this. Again, this is in the moment really the major focus of the research of all of those who follow this scenario, and I'm very hopeful personally because we have made a lot of progress. One measure of progress is probably that we can get a lot of money for it in the moment to work on it. So that might not be the best measure of progress, but it's one measure of progress which is very objective. Anyways, so what GR would tell you is what I have depicted, that if you follow your patch, your physical patch backwards in time, at some point your equations break down. And this is a singularity problem. So while during the contracting phase we could get everything out what we wanted from the scenario just by assuming general relativity, we know that we have to modify general relativity. Namely, we have to violate a very simple condition, which was written down by, probably most famously by Penrose and Hawking in their singularity theorems. And it says the following. If you follow our universe, and you recall I was denoting the patch size always with h-1, then the inverse patch size is always decreasing in a general relativistic universe dominated by what Hawking or Penrose would call reasonable matter, which is matter or radiation. So in some sense, one way of understanding it, in an expanding universe, the energy density always shrinks. In a contracting universe, the energy density always grows, according to Einstein gravity. And this is the so-called null convergence condition. It's a statement, again, about geometry. what does your horizon or inverse horizon do? And this is the bounce. So in order to bounce, what you have to do is, obviously you have to modify relativity, and you can do it by quantum or by classical measures. And just let me tell you what my philosophy is here. And this is what me and my collaborators are following. I'm a cosmologist, so I'm willing to go from bottom up. I want to ask, but only when I can compute it. So what I want to ask is how far we can get with so-called good effective theories that are fully computable classically. So I'm looking at theories that admit a desired solution, a transition from a contracting to an expanding phase at energy densities lower than the Planck density, and are considered good theories in the sense of I don't have to worry about quantum corrections blowing away my leading order classical solution. And just so you can imagine it, what we are really doing is the main feature of GR, apart from obeying the null convergence condition, is that while geometry and energy density or stress energy are intertwined, you can still separate them. Just think of the left and the right-hand side of the Einstein equations. When you modify gravity in a way as we are trying to do it, we break this separability. What we do is we braid, and this is how people also call these theories braiding or braided theories. We braid here the scalar or the scalar field kinetic energy with geometry in a way that you cannot separate them anymore. And as a result, we are now, and let me close with this statement. Obviously, this would become too technical at this point, but we are not that far that with whatever people believe was difficult or not possible with pencil and paper, we have shown that this is possible. The solutions, you show a solution and follow small deviations from the solution, so you do perturbation theory, and what happens is everything looks fine. But these are very nonlinear theories, so what we are working on now is the same what we have been doing for the contracting phase. We want to study the non-perturbative regime, and for that we use exactly the same methods as we have been using so that I could show you that simulation. We use numerical general relativity. And our hope is that within a year or two, we will either know, numerical relativity and mathematical relativity will either have taught us that there is some fundamental problem with really all reasonable classical classes of theories that would make a fully computable leading order classical transition possible, so that you are back to the fact that you have to get a quantum solution that either gives you a good bang or a good quantum bounce, or we actually will be successful, and this is how it looks in the moment, and this is really my hope that we will be, and then observations will tell us whether we are right or wrong. So if I now go back and ask a question, what happened 13 billion years ago, then this is obviously still an option, and we have to figure a theory for it. But alongside of it, and this was really my aim to convince you, there is an alternative. And there is an interesting alternative. And whatever we learn from this alternative, it might be it gives us a complete scenario that we can test observationally, depending on how successful we are with the bounce model. In the moment, again, it looks very good. And that comes with a cost. That was with the price of being able to solve by an alternative way the smoothness problem, the cosmic singularity problem, the flatness problem, the hot and cold spots problem, that they are there. It gives you predictions, and you are not stuck with the multiverse. So I consider this is a really intriguing alternative and worth working on, and my hope is that you will keep watching out for it and will follow up progress. Thank you.
Thanks. It's very interesting. I have a question. So you solve several problems, but don't you create another hierarchy problem in the sense that you started with epsilon much greater than 1, then at some point it shrinks to much less than 1 to explain inflation, and then it sort of levels out at the value of the order of 1. So you have to now explain these two extremas, right?
Yeah, so thanks for the question. Obviously, I was not careful enough to emphasizing, in my scenario, there is no inflation. So I generate all the features of the universe in this preceding contracting phase with a large epsilon, which will transit through this transition phase, and then you continue with radiation domination. So what I do is what's happening in these scenarios. Most of you are familiar with the fact that when inflation stops, it is the same here. And this is also a subject of research of many cosmologists. One has to have a reheating mechanism. So you make the energy density that drives your, be it inflation or contraction, decay into the standard model particles as we know it and into dark matter. And so that's what's happening after this scenario, but then it continues with radiation domination without inflation. So I don't ever go down to epsilon being less than 1. Thanks.
So the existing bang creates a series of waves that matter is then created out of as stars blow up and contract and blow up and contract. So where was matter before the bounce?
Thanks for the question. So it's part of the same answer. Part of the answer to your question is part of the answer that I gave to the previous question. So we imagine that ordinary baryonic matter is a result of this reheating scenario that is the result of the, let's say in this case, a scalar field that were driving the contraction and the bounce decayed into it. So the answer is it was stored in the energy density in a different form in the scalar field that was driving the contracting phase and the bounce.
Just wanted to ask about the simulated or the simulations you had. Were those regions with that are shear and curvature dominated? Would that leave any kind of observable signature now?
Very good question. So this is obviously one reason for going after this was to show how generic it is in other ways, exactly what you're asking for. So you ask is, are there the regions, and let me run the simulation because then you will see it. Are those regions that look weird? And you touched here on a problem that I could give a seminar on. Are these regions that look weird for any reason interesting? And the answer is absolutely. For 2 reasons. First of all, yes, if the anisotropies are small or shear is small but not bothersome for the smoothness, that can, for example, generate primordial black holes. So that's one of our hopes. That's why we do the 3D simulations, that if they were, relatively small compared to the horizon but survived the bounce, then this would be something that you wanna see. A second is, if I may add to it, it's a really old mathematical problem there hidden. So there is a so-called problem, the BKL or mixed master chaos problem, that was discovered by Lifshitz and his collaborators Belinsky and Kaletnikov in 1947. And they asked us, and their reason wasn't obviously related, they asked, what happens to space-time when it approaches a singularity? So if you reverse an expanding phase, it contracts. And how does the evolution look like? Do you race to the singularity, or does something else happen? And what one figured, this is what happens. So anisotropy takes over if you don't add anything. So here I added something. But if I didn't add anything, when you extrapolate backwards in time, radiation matter become unimportant, and everything what becomes important going forward, short of such a scale, smoother, you become anisotropic, and you become chaotic because in different directions of space-time, typically two space-time dimensions expand and one contracts. And the one question was, can I simulate that? That was solved about 10 years ago by one of my collaborators, David Garfinkel, and in vacuum. And the second question was, there is a second, more interesting mathematical question, and this is also a source of phenomenology possible. Do you see those? Oh, sorry, I cannot show it. Do you see these crinkles? These are the so-called mixed master spikes. So there is not just that there are regions that are dominated by anisotropy, neighboring regions behave differently. And between these regions, and these are the famous problems of BKL, evolves these spikes. And the only reason why you don't see them here is it's a resolution issue. So there are the regions between separating the differently evolving shear-dominated regions evolve spikes. And these are the other things that we are studying now with adaptive mesh refinement using numerical codes to see whether they vanish, so that contraction really could smooth out everything with a little anisotropy, or whether they are a source of phenomena too. So this was an excellent question. Thank you.